What's up, guys? You might think that I'm just chilling here at the beach in California, enjoying the warm weather. I heard we got snow back home. I don't know. You might think I'm out here just partying it up and not thinking about you guys at all. Well, you know what? You'd be half right. I'm partying it up, but I'm also definitely thinking about you guys. Want to make sure that we get some good stuff done today, okay? If any of you saw my announcement that I posted last night, and then I promptly deleted this morning, I was like, what the heck? Why does the video only have 12 views? What is wrong with you guys? And then a couple people pointed out to me, hey, Miss Mitch, we watched it as a class. I'm like, oh, smart. And then I had to go delete my announcement. So anyway, I'm glad that I was kind of freaking out over nothing. You guys are the best. I really miss you. Let's check this out. We're going to look at, real quick, 3 differential word problems. Because to be honest with you, this is where these are going to come up more than anything else, I think, okay? So this is an example of a differential FRQ. All right? Okay, so check this out. Beginning of 2010, a landfill contained, 1,400 tons of solid waste. The increasing function W. Now, as I read through here, you guys, I'm like, increasing function. I feel like that's going to be important later. I don't know. Okay? It models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation. dW dt is 1 over 25, W minus 300 for the next 20 years. W is measured in tons. T is measured in years from the start of 2010. Okay, let's start with part A. Use the tangent line to the graph. Before I even read anymore, what am I going to write down? I hope you guys are answering these questions instead of just sitting there awkwardly not answering. All right, here we go. Y minus y1 is mx minus x1. Now, what does this all represent? Now, in this case, okay, x is actually the t variable, right? And so we've got like time, tangent line at time equals 0. Time equals 0. There's a tangent line, okay, cool, of the graph at time equals 0. When time is 0, what's the y value? Now remember, W is basically the y value. We have like an equation here, W in terms of t, the amount of waste in terms of t, right? At time 0, okay, it kind of told me right here. It's 1,400. And then I need to find the slope. Well, what's the slope in terms of W and t? Slope is a derivative. It's dW dt. Okay? So let me go ahead and use that. It's 1 over 25. W is 1,400 minus 300. I actually don't know if this is a calculator problem or not. So it's 1 over 25, and then that's 1,100, which is going to give me 44, I think. Okay? And so here's the equation of the tangent line. Y minus the y value equals m x minus the x value. Okay? There we go. Now, is that the final answer for part A? Let's make sure I got my final answer. Use the tangent line to approximate the amount of waste that the landfill contains at the end of the first 3 months, time t equals 1/4. So it wants me to use this to approximate t equals 1/4. Oh, and by the way, instead of y and x, I probably should have put w and t. That's not something they're going to like dock you for, but here we go. Okay, at time t is 1/4. Here we go. W minus 1,400. So I'm approximating it. 1/4 minus 0. Okay, so 1/4 of 44, that's 11. And if I add 1,400 to both sides, that's 1,411. We always want to use labels, units. We always want to label with units in our FRQs, right? So, waste is measured in tons. Tons. There we go. Okay? All right, so I use the tangent line of the graph and I approximate. So basically it's like set up a graph, and it's like, let's say like the equation's like this or something, and this is time equals 0, and we made a tangent line to the graph, and we used that tangent line to evaluate it at 1/4, and we were just like, well, 1/4 is close enough, I'm going to use that even though the point's up there, you know? So that's why it's an approximate use of the tangent line. Okay? Cool. Let's look at part B. Find the second derivative in terms of w, and then use it to do something. Let's find it first. All right, check this out. Okay, the second derivative is, okay, so it's 1/25, right? Because constants are allowed to stay out front. And then you guys, what is the derivative of w? W prime, right? And what's another way of writing w prime? dw dt. And what's the derivative of 300? 0. Okay? So the second derivative is 1/25 dw dt. Now, really quick, though, read this. Find d2w over dt2 in terms of w. That means there's only supposed to be w's here. Okay, but what is dw dt? What? Check it out. That's dw dt. So if I plug that in, here's actually my answer. My second derivative is 1/25 times 1/25 times w minus 300. Okay? So that's like a what, 1/, I mean, I want to just put 25 squared. I think it's like 625. Okay, so that's my second derivative. All right. Use that to determine whether your answer in part A is an underestimate or overestimate. Under or over. Okay, so you would get a point or two maybe for this. We're going to actually look at the point breakdown in just a second. Under or overestimate. Okay, let's see. Do you guys remember we talked about under and overestimates? Let's think about this for a minute. All right. Let's say I have an increasing graph, and let's say it's like concave down, right? Okay. Then the second derivative, right? The slope, we could tell if it would be an under or an overestimation, right? Let's say I had an increasing and it was like concave up. We could tell if it would be like an under or overestimation. Okay? 1 second. Let me check out the points on this one. Okay, so you guys remember back up here, I said we're going to need to come back to this. This is an increasing function. So w is constantly increasing. Okay, now I don't know what the concavity is, but I know it's constantly increasing, right? Now, when I made, okay, it says we want to see if part A is an under or an overestimation, okay? Okay, we know it's increasing. We need to know if it's concave up or concave down. Now, in part A, I was using time equals 0, w equals 1400. So let's go over here. I don't have a place to plug in time. So it's 1/625, 1400 minus 300. All right. Do I need to calculate that all out? No. I just need to know if it's positive or negative. Well, this is going to be a positive value, which means that w is not only increasing, but it is concave up. So it's like that, okay? Now, what this tells me is that in part A, when I did the tangent line to the graph, the approximation, like whether it's here or here, but it's actually, remember it was 0, 1/4, is actually an underestimation. And then you can just show, or you can say because w is increasing and concave up because d2w dt2 is greater than 0. All right? Like it. Okay. Okay, now here's where, this is what we're like practicing. This is what we were doing yesterday. Find the particular solution. That means like the exact, okay? We're going to find the exact equation. to that differential if it has initial condition 0, 1400. So that's what we've been talking about, times 0, 1400. Okay, so this is where we go. Okay, so this is 1 over 25 W, oops, parentheses goes there, W minus 300. Okay, do you guys remember we were working on this a little bit yesterday? It's like, what we need to do is we need to separate the variables, all right? Anything with dt, I need to bring it over here. Okay, so dt is going to go to this side. Anything with w, I need to bring it over here. Okay? All right, now here's the thing. Move the dt over here. Okay, now the 1 over 25, I mean, you can really put it wherever. I'm going to just go ahead and leave it on this side. It like makes a little bit more, sense to me to leave it there. And then the w minus 300, I'm going to take that and divide it over here. Does that make sense? I'm like dividing that by both sides, okay? So this one's going to be over w minus 300. And now I'm in a position where I can go ahead and take the integral, separating the variables to find w, all right? Okay, check this out. Let's do this side first. Technically, this is a u sub, right? U is w minus 300. du is 1 dw. What that means when you get like du is 1 dw, it means you don't have to put anything on the outside. So we can just integrate this like normal. What would the integral of 1 over u be? ln of u. So this would be the ln of w minus 300. Okay? Let's integrate this side. Different color, keep track of this. What's the integral of a constant of 1 over 25 dt? Well, we know the integral of, like, say before we were integrating like 4, and the integral would be 4x, right? Okay, this is 1 over 25t. And then remember, we don't need to put the constant on both sides. We just need to put it on one side. Because if I have a constant here and a constant here, like, it's just one constant. So we're cool with that. All right. Next, we want to plug in the initial condition. Okay. And remember that the initial condition was at time 0, we had 1,400 whatever of waste, tons of waste. Okay. So let's go ahead and plug that in. The ln of 1,400 minus 300 equals 1 over 25 times 0 plus c. So that's the ln of 1,100 equals c. Cool. All right. Here's my equation. So I'm going to go back to here. After I plug in the initial condition, okay, I find c. And then I write the equation, the particular solution, right? Which is, ln w minus 300 is 1 over 25t plus ln of 1,100. All right? Now I need to solve for w. Okay? Let me fix that, you guys. Jeez. Okay, we're just about solving this right now. That was ln of 1,100. I can drop the absolute value since it's a positive number now. Okay, solve for w. Let's take this bad boy apart one thing at a time. To get rid of an ln, that's e to the power of w minus 300, and then e to the 1 over 25t plus ln of 1,100. Okay? E to both sides? No, that's not right. Sorry, e to the ln of that, and then e and ln cancel out. What am I doing? Right? So this is just the absolute value of w minus 300. There you go. Okay? Now, this could be plus or minus because of the absolute values. Like, I can drop those, and then it's like plus or minus. But you guys, if I were to plug in at time equals 0 and I need to get w is 1,400, is it the plus or the minus? Well, look, if time is 0, okay, e to the, e to the blah, 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 time is 0, e to the ln of 1100 is 1100, and that equals 1400. It's positive. Like, I ain't worried about that. So that's going to be positive, okay? All right, by looking at my points. So now to solve for w, w is e to the 1 over 25t plus ln of 1100 plus 300. So I need to write that a little better. That is my equation. Okay? Now, let's take a second and let's look at how the points play out for this one, all right? Okay, let's see here. I believe it is. Okay, here we go. All right, let me make this a little bit bigger so you guys can see it. Okay, zoom in a bit. All right, so there's my question. Okay, so look at part A right here. Follow this along with me. Okay, we got a point for finding dw dt at time 0. So if you got to that 44, where you found the derivative at time 0, where you plugged in 1400, that's a point. We got a point for writing, not for the tangent line, for approximating it and getting 4111 tons. All right, so that one was 2 points. That's how that broke up. Okay, this one, you get a point for the second derivative, and then a point for the answer with reason. So even if you couldn't get the answer, I mean, you guys, just by getting a point, like, for the first part, that's really good, okay? All right, now check out this last one. 1 point for separating the variables. So just for doing that, you get a point. Beautiful, right? We can all separate variables. That's cool. 1 point for the antiderivative. So 1 point for integrating that. 1 point for finding c. There we go. 1 point for using the initial condition. Constant of integration. I think that means 1 point to put plus c, and then 1 point to actually solve for c. I don't know. And then 1 point to solve for w. Now, you guys might notice that they dropped the 1100 down here as a coefficient. I'll explain that to you in just a second. And then they come up with the equation. So, but the way we had it was perfectly fine, all right? And then it talks about, like, the most you can get is 2 out of 5 if you didn't put plus c. Because then that, you can get 0 out of 5 if you didn't separate the variables, okay? So we got to make sure we do all that stuff. All right. I'll just show you really quickly. This would be okay, but just for those of you that are, like, interested here, check this out. If you have an e and it's something plus something, think about an exponent, right? Let's go back to our exponent rules. X to the third, times x to the fifth is x to the eighth, right? Which is x to the 3 plus 5, which means we can go backwards. If we're adding two things in the exponent, we can split them up, right? So e to that plus that is actually e to the 1 over 25t times e to the ln of 1100. But then, cool, what's e to the ln of 1100? Boop, boop. That's just 1100. And then they just put the 1100 out there, plus 300, and they got that for w, okay? Do you have to do that? No. But, you know, as long as you get the equation, you're chilling. Okay? Okay, that one was fun. Let's look at number 2, the boiling potato problem. Holy crap, this is a lot of words. That's a lot of words. Okay, at time 0, a boiled potato is taken from a pot on the stove and left to cool in the kitchen. The internal temperature of the potato is 91 degrees Celsius at time 0. Okay, so that's important. The internal temperature of the potato is greater than 27 for all time, so it never gets cooler than 27. The internal temperature of the potato can be modeled by the function, blah, blah, blah. Like, you guys, when you see that on an FRQ, you're like, oh, great. Separation of variables, right? Where h is measured in degrees Celsius, h of 0 is 91. It's saying the exact same thing that said. Okay, that was a lot of, like, words for not a whole lot of information. Basically, I just needed this and this. Okay. Part A. Write an equation for the tangent line at time 0. Use the equation to approximate. Gosh, does that look familiar? It's like pretty much the exact same thing we just did, right? So you see a lot of times if they choose to test you on a differential problem, it'll kind of follow the same process, you know? All right. y minus y1 is mx minus x1. Okay. We're using that. 0 is the x. 91 is the y, and we need to find the slope. Slope means derivative. So dh dt, that's the slope, is negative 1/4 h minus 27. 29, 30, 31, 64. Oh, that's lovely. That divides nicely. 10. Oh, you guys are screaming at me. 16. Okay. Negative 16. Just to not be confusing, instead of x, I'm going to go ahead and use t for time. And instead of y, I'm going to go ahead and use h for hot, right? The heat. All right? We're chilling. You can leave it exactly like that if you want. You could add the 91 to the other side and look like fancy, but you don't have to do that. There we go. Oh, that's not my final answer, though. Use this equation to approximate the internal temperature of the potato at time 3. So at time 3, using this line, that's going to be negative 48 plus 91. So the internal temperature is going to be 43 degrees Celsius at time 1. Okay? Cool. Pretty straightforward. So that's the tangent line. So again, we had like some equation and we're finding the derivative and we're just like approximating it, like going like that. And this is like time 0 and then this is like time 3. Okay? So we're using the line to approximate it instead of the curve. Use the second derivative to tell if it's an under or overestimation. Oh my goodness, same exact thing, you guys. All right, second derivative time. Here we go. Negative 1/4 h minus 27. All right. dh dt. Negative 1/4 h minus 27. Okay, second derivative. So the negative 1/4 can stay. The derivative, so remember, just like we did in this last one, the derivative of h is dh dt. You don't have to write this, but just so you guys are cool. The derivative of 27 is 0. So the second derivative is negative 1/4 dh dt, which, again, I'm going to do negative 1/4 h minus 27 to get it all in terms of h. So it's positive 1/16 h minus 27. This is the second derivative. Now, in order to tell if something is an overestimation or an underestimation, we need to know if h is increasing or decreasing. We also need to know if h is concave up or concave down. Okay? So I want you guys to think about this for a minute. This is where you kind of have to know what the problem's talking about. Because did it ever tell me that h was an increasing function or decreasing function? It never told me. But what are we talking about, you guys? We took a boiled potato from a pot. Boom. We put it here. Is this thing getting hotter? Or is it getting colder? Right? And it tells us right here, it's being left to cool in the kitchen. So what can you tell me about h? H is decreasing. The temperature has to be decreasing because the thing is being left to cool, and it's not like it's going to get colder and then all of a sudden start getting hotter again. That would be insane, right? So h is decreasing because the potato is cooling down. Now, is it concave up or concave down? At time 3. Okay, we just said that at time 3, h was, because we got to find out if this is an under or an overestimation, 43 degrees Celsius. So at time 3, okay, the second derivative is 1/16, 43 minus 27. And it doesn't really matter other than just to know that that's positive. So because the second derivative is greater than 0, this tells me it's con h is concave up at time equals 3. Maybe not everywhere, but like at time equals 3, right? So look, this is time 0, this is time 3. Except for that's not time 3 because it's a decreasing function, right? So the potato is cooling off, but it's also concave up. So I estimated this, right? I estimated time 0 with a tangent line. Is this an under or an overestimation? This is for sure an underestimation. Okay. All right, because it's because basically I'm just trying to show that it's decreasing concave up. Cool, cool. All right. Part C. For t equals 0, an alternate model of the potato at time t is a function that satisfies this differential equation. So it's like a different method. Same thing, it still starts in 91. What's the internal temperature at time 3? We got to write an equation for this. Not actually using a tangent line to approximate it. We actually have to solve it. And you guys, if this is part C, what are we thinking we ought to do? Separation of variables. All right. Okay, check it out. Let me switch over here to that. Okay, dg dt is negative g minus 27 to the 2/3. G of 0 is 91. Find an expression. Let's do it. Okay, separate my variables. I'm going to bring all this over to this side with the dg. Okay, I'm going to move all this down here. And I'll leave the negative with the dt just because, you know, so we don't have it be so lonely. So the dt will move up here. This will be g minus 27 to the 2/3 down here. Okay? So, step 1, separate the variables. We're probably going to get a point for that. That's what I'm guessing. We're going to get a point for that. Second point, integrate both sides. All right. Now, again, this is like kind of U substitution, you guys. But when you do U sub, okay, if U is G minus 27 and DU is DG, right? I mean, it's basically the same thing. So like my point is you don't have to do like 2 1/2 or something like that. Now, how do we integrate something when the 2/3 is on the bottom? Y'all remember this, yeah? We're really integrating U to the negative 2/3. And in an integral, we add 1. So it's U to the 1/3 over 1/3. We don't write it like that, right? We write U to the 1/3 times 3 over 1. And so this integrates to, okay, 3U to the 1/3, and U is that. All right? Now, this is dt. I'm basically integrating -1, so let's integral that. It's negative t plus a constant. I'm going to get a second point for integrating those, and I think probably a third point for putting plus c. Now we have to actually find c, and how do we do that? We use this, okay? At time 0... Shoot. My bad. That said G, not T. At time 0, it's 91. That's 91. That's 0. Okay? So 3 times, for heaven's sakes, 31, 41, 51, 64. It's late, guys. It is late. It's like 1:30 California time, which means it's like 2:30 your time. I sure hope you guys are sleeping. Sheesh. Okay. What's the cube root of 64? 4. Dude, that's so dope. C is 12. Love that for us. Okay, here's my equation. Here we go. Coming from here. 3 G minus 27 to the 1/3 is negative t plus 12. Yeah, we gotta freaking solve that. Ugh, such a pain. Divide everything by 3. So it's basically negative t over 3 plus 4, right? I should divide both those by 3. How do I get rid of a 1/3 power? I just go to the third. So g minus 27 is negative t over 3 plus 4 to the third. So g is negative t over 3 plus 4 to the third plus 27. Let's go. I believe it asks me to do one more thing. Find an expression for g of t. Boom, done. Based on this model, what's the temperature at time 3? Okay, at time 3. All right, g is negative 3 over 3 plus 4 to the third plus 27. That's negative 1 plus 4. That's 3 to the third plus 27. 20 plus 7 plus 27 is 54 degrees. What are we in? Freaking Celsius? Okay. Who even uses Celsius? You know what I'm saying? But check that out, you guys. I'll see how we did. All right, let's see how we did. Okay. Oh, no, I want to open up question. Sorry, question 2. Here we go. All right. Okay, for part A, all right, 1 point for finding the slope at negative 16. That's cool. That's great. That's a point. 1 point for the tangent line, okay, which we got like right here. And then 1 point for the approximation, which we got 43 degrees Celsius. Cool, cool. For part B, 1 point underestimation with reason. That's kind of crazy because we freaking did a lot of work for that. So that bugs me, but whatever. All right. So basically what it's saying is like, finding this, see on the last problem it gave us 2 points for this part. This is only giving us 1 point. Whatever. Because we knew that it was decreasing concave up, the answer is an underestimate. So underestimate with reason. Okay. Woo, 5 points. We love this, right? Check it out. Separating the variables, boom, that's 1. Taking the antiderivatives, boom, that's 1. Constant of integration and uses the initial condition, that's finding C, boom. Equation involving g and t. Boom. And then finding g of 3, 54. There's where your point breakdown comes. Okay? All right. Last question. The legendary baby bird problem. All right. I don't know why it's legendary, but okay. The rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. Whatever. At time 0, when the baby is first weighed, its weight is 20 grams. Okay, I'm going to write that down. B, the baby bird's weight at 0 is 20 grams. Oh, it's so cute. T is time days after it's first weighed, and I have a differential. Let y equal b of t be the solution of the differential equation above with the initial condition. Oh, that's cool. I don't really need to write that down. Whatever. All right. Is the bird gaining weight faster when it weighs 40 or when it weighs 70? Explain your reasoning. Gaining weight faster. Let me think about what we think that means. I think, I haven't looked at the points for this just yet, so let's do a little test and see how we do, right? Okay. dB dt would need to be positive. That means it's gaining weight. Okay? Now, if the second derivative, I guess I would say whichever one is bigger would mean it's gaining weight faster. And you know what? You know how I'm like thinking about that, you guys? I'm actually thinking about the physics stuff because I'm like thinking, okay, gaining weight would be like velocity. Gaining weight faster would be like acceleration. I'm thinking, you know? So, all right, cool. Okay, so I don't think we actually, well, I suppose we can see if it's gaining weight or losing weight, right? So let's see, dB dt is 1/5, 100 minus 40 grams. So, okay, so this is at, let me just write this down, at 40 grams. All right, at 40 grams. So the first derivative is a fifth of 60, which is like 12. He's gaining like 12 grams per, is it days? I gotta read this back. Time 0. Oh, for goodness sake. T is time t in days. Okay, sorry, that took me forever to find that. Okay, now, well, let's find the second derivative real quick, shall we? Actually, do we need the second derivative? I don't think we need it for this part. I don't think we need it for this part. At 70 grams. Okay, equals 1/5. 100 minus 70, which is 1/5 of 30, which is 6 grams per day. I think that's all we need. It's we actually don't need the second derivative, you guys. I was mistaken. It's gaining weight faster at 40 grams. Okay, because the derivative is more grams per day. All right, cool. Now, for the next part, though, we definitely do want to find the second derivative. Find the second derivative in terms of d. Explain why the graph cannot resemble the following graph. Okay, cool. Let's see. db dt is 1/5 100 minus b. Second derivative is derivative of 1/5 is 1/5. The derivative of 100 is 0. The derivative of negative b is negative db dt. Ooh, a negative. Okay, so it's 1/5, and then it's negative 1/5 100 minus b. Yeah. I don't know. Okay, so my second derivative is negative 1/25, 100 minus b. Okay, now, why can't it look like this? Well, let's go ahead and find, okay, well, first thing I know, b is always increasing. So if I'm doing like increasing or decreasing, well, is that true? Let's see here. Let's look at a sine line graph for the first derivative, okay? Now, when we're making sine line graphs, we say, where does the derivative equal 0? Obviously, that's at 100. Anything less than 0, so like 50, that would be positive. Greater than 0, like 200, that would be negative. So the baby bird is actually increasing, decreasing, okay? Now let's make a sine line graph for the second derivative. Okay, if I set the second derivative equal to 0, that's also changing signs at 100, right? Okay, sweet. This is actually blocked off at 0 because it doesn't go before that, but whatever. Okay, so at 100 is where it's changing concavity. And let's pick a number less than 100, like 50. That would be a negative times a positive. Let's pick a number over 100, like 200. That would be a negative times a negative. So that is concave down, concave up. Okay, so I'm going to say that from 0 to 100, my function is increasing and concave down. From 100, actually, we don't know where it stops, do we? Does it say it stops at a certain point? No. So actually, bigger than 100, what's happening? It's decreasing and it's concave up. This does not match the graph, because if you guys look at this graph right here, this is increasing concave up. This is increasing concave down. And that does not match what I got. Okay? So you'd use that to explain. Separation of variables. Let's go. B of 0 is 20. you guys are seeing that this is like the same steps. I mean, kind of. That last question was like kind of interesting. Part B, that was a little bit different. But, okay, separation of variables. Let's see here. dB dt is 1/5 100 minus b. Okay, check it out. I need to put this one down below with the b, and I'll put the dt over the 1/5. So I'll go dB over 100 minus b is 1/5 dt. Now here's the thing, you guys, okay? This is actually u sub, like I was saying. And usually I'm like, you can kind of ignore the u sub, whatever, we can just do it. You can't really ignore the u sub right now. You got to pay attention to the fact that, like, if I use a u sub right here, if u is 100 minus b, du is negative dB. Okay? So as long as you recognize that there's going to be a negative there, so then that's 1 over u du, which is ln. Negative ln of u, which is negative ln of 100 minus b. Okay, so we do have that negative there. On this other side, well, there's really just one step, because the integral of 1/5 dt is just 1/5 t plus a constant. Okay, let's use our initial condition, which was b of 0 is 20. So my initial condition, at times 0, it equals 20. So C is the negative ln of 80. All right, C is the negative ln of 80. So now here's my equation. Negative ln 100 minus b is 1/5 t minus the ln of 80. Okay? You guys, I want to divide by a negative before I do anything else, I think. So when I divide by that negative, it'll change the sign of that and that. So the ln of 100 minus b is negative 1/5 t plus ln of 80. Okay? The way that I get rid of an ln is I e to both sides. That goes away. 100 minus b is e to the negative 1/5 t plus ln of 80. All right? To take the absolute values off, it's going to either equal plus or minus. How do I know if it's going to be plus or minus? I got to use this initial condition again, okay, to see which one. Now, if I plug in 0, okay, that's going to be e to the ln of 80, which is going to be 80. 100 minus 20 is 80, so I'm using the plus again. I'm thinking like most of the time we're going to be using the plus, right? Is that what it seems like? Okay, subtract 100 over. And divide by a negative. So it's negative e to all this plus 100. All right, are you fine leaving it like that? Absolutely, totally fine. When I go and we look at the points, are they going to do this? Probably. Okay, negative, let's just do this. E to the negative 1/5 t times e to the ln of 80. But e to the ln of 80 is just 80. Okay, so it's probably going to write it like this. Negative 80 e to the negative 1/5 t plus 100. All right. Was I supposed to do something with that? No. Done. Okay, cool. Let's check out our points on this one. Question 3. Let's check it out. Okay. So we used dB dt. We gave an answer with reason. That's because 40 is bigger than 70, faster as 40. Okay, cool. We found the second derivative. That gave us a point, the explanation. It's concave down. The portion of the graph given is concave up, so that was wrong. And then separation of variables, finding the antiderivatives, finding the plus c, using the initial condition, na of ln of 80, solving it. Okay? And that's what we got. Dang, super cool. I wanted to keep it under 45 minutes, and I did. Hooray. Okay. Oh, shoot. I only got a few seconds to say this last part. That's okay. Check this out real quick. Here we go. All right. I know that the other day I assigned you the 2012 FRQs. Okay. Today I'm assigning you for homework. There's not like any other type of homework. We're just going to start reviewing, right? The 2012 multiple choice. Okay. I am trying to get copies of those made. Hopefully those will be made for you tomorrow, right? If not, just do it on paper and write down your things. And well, like I put up videos and stuff, but we'll go over all these on Monday. By Monday, I'd really like you to have those two things done. I mean, if you're completely confused, watch some videos, see how it goes, right? I put that up there. But by Monday. The other thing is, those of you that have not turned this in yet, you know that actual big, like, practice AP test we did? Okay, hopefully most of you have done that now with the full AP test and stuff like that. Some of you did part. I told you to do the rest over spring break. Just make sure that you bring that on Monday as well. Okay? Does that sound good, my friends? I hope you're all doing good. I really, really miss you. I'm going to hit the beach one more time tomorrow, and then I'm coming home. All right. Peace out, guys. Have a great day.